Okay, so starting for a problem like this, first thing you do is you draw a diagram just to show what's going on. You can make it a lot uglier than this. Don't even bother using a ruler, honestly. Anyway, here there's what is it? There's a brass rod and two steel rods. They're hanging off of this piece over here, and there's a 5 kilogram weight underneath both of them. So the two pieces up here and down here, they're both rigid, and also this piece down here is 5 kilograms, but I'm telling you in advance, ignore it. Anyway, this also shows that there is a 2000 compressive force on the brass rod, and that is what we want to reduce that to 0 by changing the temperature. That's what the problem asks for. Anyway, step 2 is going to be just identifying all your variables. So these are given, this is also given, and then for the cross-sectional area of the steel, there's 2 steel rods. Each of them has 1 times 10 to the negative 4 meters squared. So you can just add them up. So there's 2 of them, so that's why there's just 2 times over here. And then I also wrote the length in meters. So in the question they're given in centimeters, but I find it's better to just like label them all as in SI units, because that's what you're going to be working with. Anyway, step 3 is going to be identifying your equations, or at least the relevant ones. These are the relevant ones for a question like this, where it's, change in length based on temperature. Anyway, so this is the change in length based on a temperature change, and this is, pressure and change in length, Young's modulus. So, as I was saying earlier, right now there is a 2000 compressive force on the brass rod. What we want to do is introduce a temperature change such that we can alleviate this force. A way to think about it is introducing a 2000 tensile force on the brass rod. And we'll do that with changing temperature. As you can see, based on these two values, they're different. So that means that looking at this equation, their lengths change differently based on the temperature. Anyway, so how to start this? First off, these are 2 rigid bodies, right? And these 3 rods, they're kind of stuck between them. That means that their changes in length are going to be constant, or they're going to be the same between brass and steel. So the change in length of brass is equal to the change in length of steel. And then what we can do from here... Oh yeah, I forgot. I'm going to rearrange this thing into something that's the change in length. So I'm just going to isolate change in length. So it's going to be change in length. Delta L is going to be equal to delta F times L divided by A times Y. And then what we're going to be doing is combining these two. This is the change in length due to temperature. This is the change in length due to a force or pressure. What we're going to be doing here... So the change in length is, for a question like this, we're going to be adding both of them. So what is this? So A brass, length brass, change in temperature. This is constant, this is the same for both steel and brass, so we're just going to put change in temperature, no V at the bottom. Then plus a change in force. Oh my god. Change in force times the length of brass rod divided by A brass Young's modulus of brass. And that's equal to area of steel, length of steel, change in temperature, plus delta F LB AB YB. And then now from here, about the forces. So looking at this equation over here, a positive force will result in a positive change in length. So that means, so if we're looking over here, right, what's going to happen is we're going to introduce a tensile force. So the force on the brass rod is going to be this way, and in order to sort of counteract it, the force on steel is going to be going this way. is the compressive force. So then, since the force is sort of making the steel rod length smaller, the force on the steel is going to be negative. So that's why we're going to put a negative over there. And then from here, you check, and we have, this is the variable that we're looking for. Then A, B, L, B, we have all these other variables, we have numbers for them. So you can just isolate for delta T. It's like this. T, and that's equal to negative delta F LB. Oh my god, I wrote these wrong. Yours should not be B, should be S. Sorry. Sorry about that. LB over AB YB plus LS over ASYS. It's going to be that. And then change in force is going to be 2,000 newtons because we're trying to get rid of this force over here. Another thing, the cross-sectional area, just assume it's constant. You don't need to overcomplicate it by changing this number around. It's probably negligible anyway. Alright, now you just plug in all the numbers. I'm going to be lazy on the times 10 to the negative 4. So what is it? AB 2 times 10 to the negative 5 times 0.1. That's 2 times 10 to the negative 6. That's minus 1.2 times 10 to the negative 5 times 0.05. What is that? 5.6. 0.6 times 10 to the negative 6 times delta T. Is that right? I think that's right. Okay, and that's equal to negative 200, no, sorry, 2,000 times the brass, 0.1 over 2, Young's modulus for brass is 9, and then negative 4 plus 10, that's 10 to the 6. Then plus length of steel, 0.05, cross-sectional area, times 20, times 10 to the 6, negative 4 plus 10, 10 to the 6, negative 10 to the 6. And then you just plug this into your calculator. Oh. Just move the paper a bit. So plug this into your calculator. You should have delta T equals negative 9.72 degrees Celsius. And I'm just going to double check these things over here. They should be right. Yeah, that's 0.6, right? Should be 0.2, 0.6. Yeah, because this term needs to be positive. Okay, yeah, this is correct. Alright, and then force 0.1, 2 times 9 times 10 to the 6, 0.05, 2 times 20 times 10 to the 6. Yep, that's right. Bam. Alright, so starting off with any thermodynamics problem, or any physics problem for that matter, first thing you do is you draw a quick diagram. Make it quicker than this, don't use multiple colors, that's pointless, don't draw a face. Anyway, from here, we're showing that there's Mr.Brick inside of a copper tub, and there's an 8,000 Newton compressive force on Mr.Brick. And also all of this is at 20 degrees Celsius. Step 2 is to just write out all your variables. Variables, also, they tell you about water, make sure you add that. And step 3, write out all the relevant equations. So these two are to do with change in length. This is change in length due to temperature changes. This is change in length due to forces or pressure. And then this is to do with temperature change. And that'll be in the last part of this question. So what we want to do is we want to introduce a temperature change to get rid of this 8,000 Newton force. And what we're going to be doing is we want to sort of introduce a tensile force on Mr.Brick like that and like that. So what you can do is pretend that the copper tub and Mr.Brick are like attached to each other. And then when we increase the temperature change, the copper is going to be growing faster than the Mr.Brick because of these two values. You can see this one's larger than that one, -5, -6. Anyway, what's going to be happening is the copper tub's going to be growing, and then it's going to be pulling on Mr.Brick up, and that's what we want to do. So, what's important to note is that both of these will have the same length. So that's why length is not given in the question, because it'll cancel out later on. So first thing, as you already saw what I did in the last question, I'm going to rearrange this, and I'm going to combine these two equations. So then you'll have change in length is equal to AL delta T plus delta F L over AY, right? And then what you're going to do is delta L of the copper is equal to delta L of Mr.Brick. And then you'll have, let's see, A copper L delta T plus delta F L over AY. These will be C. That's equal to AB L delta T plus, what was it? FL over AY. And then you can see all of these terms have the L in there, right? So you can just cross it out, scribble it out, whatever. And that's why length doesn't matter in this question. Anyway, what we're going to be doing from here is isolating for the change in temperature, because all of these values are given, right? Change in force is 8,000 newtons. Yeah, so I'm just going to do that right now. AB times the change in temperature is equal to, right. So I forgot something. So the change in force is going to be, one of these is going to be negative and one of these is going to be positive. And if you remember what I did in the last question, right? Just looking at this and this, right? A positive change in force will result in a positive change in length. So that means that, so since we're introducing a force to make Mr.Brick longer, that means that the force on the brick is going to be positive. And then this one will be kind of pulling on the copper this way, right? Because just pretend that they're rigid. So then the one on the copper tub will be negative. So then when we bring this term over to this side, it'll be change in force times 1 over ABYB plus 1 over ACYC. Because you change the sign and then you bring it over. Anyway, so you bring this term over there. Change in temperature is equal to plus 8,000 divided by And then I'm going to be lazy with the powers of 10 because, you know, why not? It'd be 17 minus 5.6 times 10 to the negative 6. 6, these are the A values from up there. You multiply that by 1 divided by area of the brick. 0.005 times 2 times 10 to the 10 plus 1 over 0.002 times 11.8 times 10 to the 10. Then let me just double check this really quick. 1,000. Yeah, so then you'll have a temperature change is equal to 9.991 degrees Celsius. And then now we're going to move on to part 2 of this question. That's finding how much water you need to add. So we're going to be using this equation up here and conservation of energy. So we know that Q water. Wait, hold on. One sec, where's my eraser? Here it is. So with conservation of energy change in water is equal to energy change in the brick plus energy change in the tub or the copper. I don't know why I wrote brick. And we know, and since the temperature of water is going to be higher in the start than in the end, that means this term will be negative. So what we'll be doing is negative Q of water is equal to Q brick. I don't know why I'm writing all that. Okay, I'll just write a B. B plus QC, then negative MC delta T. Is that right? Yeah. Delta T. Oh my god. M water, C water, delta T. Mass of the brick, C brick, delta T plus C delta T. Now just remember, these two will be the same, but then this one is going to be different because this has a different starting temperature. Although, I mean, you could probably justify rounding it to 10, but I'm not going to do that. Anyway, what you do from here, what is it? Oh yeah, you just plug in your values. It's negative mass water times C of water is 4,190. Okay, you can't really see it because it's a bit high up, but whatever. And then temperature change is going to be temperature initial minus temperature final. Oh, sorry, no, temperature final minus temperature initial. My bad. And the final temperature, right, so after the temperature change, the system is going to be at 29.991 because it's the original was at 20 and then you add this temperature change. So then this term of delta T for the water, that's going to be 29.991 minus 40. And this is equal to mass of the brick. I think that's 5. Heat constant, that's 800. Change in temperature, 9.991. Then for the copper tub, mass is 10 kilograms. Specific heat is 390. change in temperature is 9.991. And then you isolate for everything. Mass of the water. You just divide all of this stuff by that. You should have 1.889 kilograms, which turns into 1.89 kilograms. Alright, so starting off any physics problem, first you just draw a quick diagram of what's going on. We're only doing part A for this diagram first, and then we're going to do part B later. So, after that you write out all your variables. So, CV of the gas, 2R, so that's over there. And then the area of the piston. Where does it say that? It says you install a movable piston with a weight of 1 kilogram and a radius of 5 millimeters. You'll notice that I changed it to meters. It's always good to change it to SI units. Just because it's easier to work with and the units are nicer. Anyway, mass of the piston, 1 kilogram. Mass of the weight, that's what we're looking for right now. Temperature 2, we don't know that. We're given the height. Yeah, I also changed the height to meters. As you can see, it says over here, H1 equals 20 centimeters. It's 0.2 meters. And then pressure of the atmosphere equals 100 kilopascals. Do not forget that. This is so important. Anyway, oh yeah, I forgot. Now, step 3 is going to be writing out some relevant equations, right? And just make sure you know what to work with. And here, part A, it says settles very rapidly. That tells you that this is an adiabatic compression. So, what are the adiabatic equations? Also, first off, this just with any ideal gas equation, always write out the ideal gas law. I think that's what it's called. PV equals nRT. Always draw that. That's always good to have in your back pocket, even if you don't end up using it. Anyway, looking at our equation sheet, what do we have? These are the adiabatic equations. So PV, let's just be writing it here. PV to the power of turnip is constant. And TV to the power of turnip minus 1 is constant. Also, we have that the turnip is equal to CV plus R divided by CV. It's the same as CPE over CV, but this is a little more obvious to work with. And also, we are going to be working with pressure. I'm just telling you that in advance. So we're going to add this thing over here. And now we're going to actually start the question. So, we're trying to find the mass of the brick that brought the height of the piston from 0.2 meter to 0.1 meters. What we're going to be looking at first is this equation. So, PV to the power of this is constant, right? Oh, wait, sorry. I should actually do this differently. P1 V1 equals P2 V2 to the power of the turnip. Now I should note that the volume is equal to area times height, right? And the area is the same for both of them, so we're going to rewrite this as P1 H1 to the power of turnip equals P2 H2 to the power of turnip. Also, I'm calling this turnip, but it's not, I don't remember what it's actually called. So yeah, to go from here to here, just divide by area. Area is the same for both, so that's why it's allowed. And then we need to find an equation for pressure. And pressure, that's equal to, I'm just going to write it over here to save space. Pressure is equal to, actually, yeah, 100,000. That's pressure of the atmosphere, plus force is mg, divided by the area. Okay, so pressure 1 is equal to 100,000 plus mass. The only mass on on this gas is just like the piston, so that'll be 1 times 9.81, and then divided by the area, that's pi times 0.005 squared. And here I like to punch this into the calculator because, well, we are going to refer to this later, and I mean, having a number is much nicer than having to plug this in all the time. So, yeah, you can say I worked on this earlier. 100,000 plus, do a fraction, 9.81 divided by pi times 0.005 squared. Yes, that's good. 2249. I could just do another 0 here, but I'm just going to do that. You could round it off to make it a bit faster if you want. You don't need to be that specific. Anyway, we are actually looking for pressure 2 because pressure 2 is equal to atmospheric pressure, obviously, and then plus the mass, right? And the mass on this is the mass of the piston plus the mass of the weight. So that'll be 1 plus m times g divided by area, which is pi times 0.005 squared, right? And then now plugging it into this, we have, I'm going to move this over to that side just to make things a little nicer to work with. Actually, I'm going to do times 9.81 times 9.81 divided by pi times 0.005 squared plus 100,000. That is equal to 224,904.8. And also, I'm going to move this height over to that side. So it's 2 divided by 0.1 to the power of the turnip. And now up here, I'm just going to write out the turnip. Turnip is equal to CV plus R over CV, which is equal to, so here we have CV equals 2R. So it's 2R plus R divided by 2R. Then R cancels out. It's equal to 3 over 2 or 1.5. We're going to do 1.5. Now, from here we just isolate for M. So I'm not even going to write that out. I'm just going to do that on the calculator. So you have this term, you subtract by that. Subtract by this because you're bringing this term over there, right? And then you multiply it by this, and you divide it by that. And then you subtract it by 1. So you have this number. You multiply it by the height, or the whatever. So 0.2 divided by 0.1 to the power of 1.5. That's this term over here. And then you subtract this term. And then grab all of that. I'm just going to do something to make it easier. And then pi times 0.005 squared divided by 9.81 equals 4.29228. And then that solves for 1 plus m. So we need to subtract by 1 again. And it's 3.292. So mass is equal to 3.292 kilograms. And that's A. Now, alright, now we're looking at part B. So, again, first thing you do is you draw a diagram. But we gotta read the question first. You're happy with your new scale, but when you come back the next day, you see that the movable piston is now at a different height above the bottom of the cylinder. You check again after another day, and it is still at the same new height. What is the value of H? So if you remember from any compressions, the temperature of the gases will increase. So as you saw here, the first time it was compressed, it went from temperature 1 to temperature 2. and temperature 2 increased. So then what was happening between step 2 and step 3, which is the final thing, or final state, is that the gas inside here cooled down. And since it cooled down, that means the pressure also went down. Just because ideal gas law. So I'm going to have to draw a diagram here. Give me a second. So this is between 2 and 3. So we know that 2 looks something like this, right? And I'm going to color orange in just to show that it's a bit warmer. Then that means that this one will be a bit lower than that, and it will be blue. Because it's cooler. So we already wrote all our variables up here. We don't need to do that again. And next we find our relevant equations. So going back here, you see, so you're not touching the cylinder at all. You're not like adding any gas to it. You're not increasing the temperature or anything. So that tells you that this is an isobaric compression, meaning the pressure is constant. That means that this equation applies, or delta T. So pressure is constant, N is constant, R is, well, it's a constant. Then volume and temperature can change, right? So then that also means that if you bring temperature over there and pressure over there, right, so delta V over delta T equals P over NR. This is a constant, therefore this is a constant. So this is constant. And then we also know volume is equal to area times height. Area is a constant. If you divide a constant by a constant, that gives you constant. So height divided by temperature is constant. And height's easier to work with than volume. So now what? Now we want to find. So now we have what, H2 divided by T2 is equal to H3 divided by T3. Let's just gotta make sure you can see all this. Yeah. T3. So we have H2, we have H3. We're looking, we have H2. We don't have H3. T3 is actually the same as T1, and we don't have T2. But T2 we can find, because if T2 is at the end of an adiabatic compression, and if you look back up here, we still have this equation up here. So, what is it? Just finding T2 V2 to the power of this is equal to T3 V, not 3, 1. T1 V1 to the power of this minus 1. So then, T2 is equal to T1 times H2 over H1 divided by, and again, I'm simplifying this down to H because, you know, you're just dividing this by that. And then remember, it's volume is equal to area times height. Area is the same for both of them, only height is different. So you're kind of just bringing out the A. Anyway, so the temperature we have is 20 degrees Celsius. But when you're working with like ideal gas law, the temperature is actually given in, or it's supposed to be in Kelvin. So temperature 1, that's actually 20 plus 273.15. That's the conversion from Celsius to Kelvin. And then you multiply this. Height 2, that's equal to 0.2. Height 1 is 0.1. The turnip we solved up here is 1.5. So 1.5 minus 1. And the temperature number 2. Plug it in. Let's see, 293.15 times 0.2 divided by 0.1, power of 0.5 equals 414.577. Alright, starting out any physics problem, as usual, you have your diagram. First, the gas is cold and it's pretty compressed, and then the elevator is all the way down here. And then step 2, which is final, that's where the gas is all heated up and it's kind of expanded. And then the elevator is all the way up here. Right. Then step 2 is you write out all your variables. Just read through the question here. So ECV equals 5/2R, a large cylinder with a freely movable piston top. We'll get to that later, but this is one hint that this is an isobaric expansion. Anyway, moving on. Cross-sectional area of 0.2 meters squared. A equals 0.2 meters squared. Height, initial height 1 meter. Initial temperature 300 Kelvin. Right. Mass 250 kilograms. Atmospheric pressure 100 kilopascals. Remember that. Then I have to write the rest of this by hand because it didn't print out properly. Anyway, we have power is equal to 2,000 watts, and we have a height final of 4 meters. Should probably write that we do not have a temperature final, which we will be looking for. Anyway, also note this part, assume no heat enters or leaves the cylinder except through the bottom. This just makes our life easier. Yeah. Anyway, so step 3 is to write out all your relevant equations. So you remember this is a freely movable piston top. Another thing to note is that there's no change in pressure. There's no change in outside pressure, so it's just fuel sitting on the piston, and also the atmospheric pressure just pressing down on it. So that's how you know that it's isobaric, and because it's isobaric, it means P delta V, remember P is constant, is equal to NR delta T. Right? Then what else? So we want to find how much energy is needed to expand the gas from here to here. Right? And this is going to be energy applied to the gas, so that's going to be Q, because Q is just heat applied to gas, right? So equation for Q is equal to NCP delta T, and also, actually, that's all we need. Yeah, so right now we want to find Q, and we have CP because CV, we'll get that later, right? And then for a change in temperature, we need temperature final minus temperature initial, right? Or we could just solve delta T with this equation over here. We also don't have N. So with N, I think we're going to find N first because it's actually quite simple. So if we rearrange the ideal gas law to just get rid of the deltas there, then that's equal to PV over RT, which we have at some point. So we can look at the initial things, right? So pressure is equal to the atmospheric pressure, so that's 100,000, plus the pressure of the mass of the piston and fuel. So that's the mass, 50 kilograms multiplied by 9.81. That's the gravitational acceleration. And then you divide that by the cross-sectional area, which is 0.2. Then this will give you, if we pull out our calculator, because you don't want to do this in your head. It's just not a good idea. It's 100,000 plus 250 times 9.81 divided by 0.2. And that gives you 112,262.5. 5 pascals. And right now we're given like a height in meters and an area in meters. So that's why we're going to use pascals. If we were given like a volume in liters, then it's better to use kilopascals. That's because of the way the unit conversions work. This will give us joules if you multiply it by a volume in meters cubed. All right, so we have pressure, right? Volume at the time. Volume is equal to area times height, right? So then that's 0.2 meter, 0.2, and you multiply that by the height initial. We're going to look at the initial because we have temperature initial, right? Height initial is 1, so volume is 2 meters cubed. Okay, and then we look at the temperature. We have 300 Kelvin. That's 8.31. So N is equal to 112,262.5 pascals. Multiply that by 0.2 meters cubed. Divide that by 8.31 multiplied by 300. That should give us, all right, try not to get much clear there. Okay, 112,262.5. Just gonna, no, not that one. This one, bracket, multiply by that 0.2, then divide that 8.31 times 300, 9.006. 0.00, yeah. 9.006, 217. That's, you don't really need these 3 digits, but that's fine. All right, and this is in moles, I'm pretty sure. Anyway, and then now we can solve for delta T. Actually, we could have solved delta T earlier. I forgot something. So, because this is isobaric, right? That means we can rearrange this to say delta V over delta T equals nRT. No, wait, sorry. nRT, my bad. What is it? nR over P. And we know that pressure is constant. These two are also constant. Therefore, volume divided by temperature is constant. So that means that volume final over temperature final is equal to volume initial over temperature initial. And that means that temperature final is equal to temperature initial times, what is it? Volume final over volume initial. So I'm just gonna be a bit lazy here and show my work. Just leave it a bit messy, that's fine. Temperature initial, that's 300. Now this is volume final divided by volume initial. Area is the same for both of them, so we can just use the height. So we're just gonna do the height final minus height initial. So that's 4 meters divided by 1 meter. That's 1200 Kelvin. Right? And then remember delta T is is the temperature final minus the temperature initial. So delta T is equal to 1,200 minus 300, so that's 900 degrees Kelvin. I'm just gonna move the paper a little bit. Now remember we're trying to find Q over here, right? So remember that Q equals NCP delta T, right? We have N, we have delta T, CP equals CV plus R, so that's equal to 7/2 times 8.31. Remember R is equal to 8.31. So then Q is equal to 9.006217. That's N multiplied by 7/2 times 8.31 CP, and then multiplied by 900, which is delta T. Then that gives us this times 7/2, 8.31 times 900. Right, and you just press enter here. What is our energy? Equal to 23575, 1.25 joules. Right, and then you're trying to find a time. So remember, power is equal to energy over time, right? So then time is equal to energy over power. So you just divide, what you do is you just divide this number by our power. And remember our power up here is 2,000 watts. So divided by 2,000 is 117.18, 117.876 seconds. I'm just gonna write those letters too. Oh, I'm sorry, you can't see. Yeah, it's that. And then on the answer key, it only shows with power like 3,000 and 3,500. So I'll just show you, if I change the number of power to 3,000, right? Then you'll get T equals 78.58 seconds. Yeah. And that's our answer over here at 3,000 watts. Yep, and that's it. Alright, so this is a question that popped up in the multiple choice section of my 157 midterm 2. And this was pretty tricky. So I had to pull out something that someone showed me for a homework assignment. And yeah, a lot of people did not get this question, I don't think. So I'm just going to read this because my writing's kind of messy. An ideal gas has CV equals 3/2R. Pressure and volume are slowly doubled so that they follow a straight line on a PV diagram. If P1 equals 100 kilopascals and V1 equals 0.1 meters cubed, what is the change in the internal energy of the gas? Right, so just starting off, you need to draw some kind of diagram. For this, you can draw a PV diagram, right? So you have, yeah, that's pretty straightforward, right? Pressure, volume, and then P initial is equal to 100 kilopascals, V initial is equal to 100 liters. I put liters because this is in kilopascals. You multiply kilopascals by liters, you can get joules. Sorry. So what do we do from that? All right. So we're looking for the internal energy of the gas, and you just write out your relevant equations. Internal energy of the gas is equal to NCV delta T. And what are you supposed to do from here? Well, there's no equation for volume and pressure changing, I don't think. Or not when they're double like that. So you have to pull out some weird substitution. So we have pressure initial, we have volume initial, we do not have temperature initial, we do not have temperature final, we do not have volume final, we do not have pressure initial. Oh, sorry, we do not have pressure final, right? But we do have the ideal gas law. So how's it going to help us? We're going to be using this thing a lot for this method. So first thing to note is that this is true for at any point. This is true at this point over here, the initial, and it's true at the final, at this point over here, right? On the diagram, if you follow. So over here it says that, oh, I should probably write is equal to 2p initial, and it's equal to 2 volume initial. I don't know if that's legible. Okay, anyway, so, and we know that P final, V final is equal to nRT final. And we know that since pressure is doubling, so P final is equal to 2P initial, and volume is doubling, so that's equal to 2 volume initial. That's equal to nRT final. And remember, this applies to, imagine that all these finals were initial, so P initial times V initial equals nRT T initial. And this is 4 times P initial V initial, nR is constant. So that means that, so we have 4P initial V initial, right? And that tells us that temperature final is equal to 4 times temperature initial. Is that legible? Yeah, it's legible. 4 times, and so delta T is equal to temperature final minus temperature initial, which is equal to 4 times temperature initial, because that's what temperature final is, minus temperature initial. So going back to this thing, we do not have temperature initial, which is what we need, but we also don't have N. What can we do for N? What we can do is N is equal to PV over RT. Now we have pressure initial and we have volume initial. What we can do is temperature initial, like that. Okay, so then when you substitute all these values in, so P is delta U is equal to NCV delta T, so that's pressure initial, volume initial over R temperature initial, multiplied by CV. We have CV, I forgot to put that down here, but whatever. I think you guys can follow, 3R over 2, and then delta T is, just going to do 3T initial. So then, temperature cancels out, and we don't need that. Also, R cancels out, so that's a bit more convenient. And then from here, yeah, from here, you just substitute values here, 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 and here, and don't forget that one. So you have pressure initial, that's 100 kilopascals. And volume is 100 liters. Remember, I changed that from meters cubed to liters. That's because of the way the conversion works. It just makes it a bit nicer. You multiply that by 3 over 2. That's a, yeah, that's a 2, whatever. Multiply that by 3. And that gives you 10,000, 4.5, 45000. And that's your answer. So, yeah, just, it's always good to remember that you can isolate for N in this thing, in this equation, and you can use it at various times. Oh, okay, sorry, you didn't miss the last part, but that's pretty straightforward, I think, from there. Yeah. And hopefully this helps.